I put this up on the board. I thought this is pretty clever. I'd never seen anything exactly like this, and so 8 solar masses is kind of the tipping point between high mass stars and low mass stars. High mass stars live short lives, and low mass stars, hey Nicole, just scoot those over there if you're in the way. And low mass stars live very long lives. And let's see, what is our sun? Is it a high mass or low mass star?
Low mass.
It is a low mass star. Very good. And we finished 13. We're starting 14. Yeah.
I think I might be misprint or something.
Oh, yeah. You need to take where it says 13 and mark through it and put 14.
Oh, okay.
Yeah. Yep. So, yep, our sun is here. So this is 1 solar mass. Looks like that. And how is our sun gonna? After it's a main sequence, what is it going to do?
It's going to turn into a red giant.
It is. If this is main sequence, oh dear. If this is main sequence, it's right about here. It's going to turn into a red giant. Okay, and then what's it going to do?
Going to keep big.
Peel off, make a planetary nebula. Yep. And then it's going to do what? What's its retired state? A white dwarf. Yep. So white. D for dwarf, and this is R for red giant. Cool. Yep, and that's our sun that we all know and love. Now, how long is it gonna be when the sun does this, leaves the main sequence?
5 billion years.
About another 5 billion years. Yeah, exactly. So, yeah, very good. So some of the times it's hard to know if it's a figure like an artist drew it or if it's a photograph. I'm thinking this is a photograph. And this is actually what we call a stellar remnant. There in the middle is a pulsar. Okay, I'm thinking this right because I've seen videos where actually it looks like a little heart beating. I know, it's so adorable. So we'll be talking more about pulsars. White dwarf. You guys told me that the sun is going to become a white dwarf. How many in here has seen the bright stars, the dog star Sirius? Yeah. I bet you have. Like near Orion, and then there's a bright star Sirius. Yeah. Okay. Sirius actually has a companion, and the companion is a retired star. It's a retired dwarf star. Okay. Now we can't see Sirius definitely outshines its companion. But can you see kind of from left to right? This left one is invisible light, and this right one I think is probably an infrared. So if you kind of dim down, look at different wavelengths, you can kind of tease out the companion star. Is that not cool or what?
I find it frightening knowing what happens with white dwarfs and the big ones.
The big white dwarfs?
Like when the white dwarf consumes the bigger star.
That's true. If a white dwarf were going to fly into a bigger star, I think we saw that in the video. That is kind of frightening.
Especially with how close it is.
Yeah, that's true. So, very good. Do I have more on the slide? I must have more on the slide because I got space for it. So the thing about the white dwarf, our sun is going to become a white dwarf, okay, the retired version of our sun. The thing about the white dwarf is its core is very compact. It's retired. It no longer has nuclear fusion going on. But it's basically over the 10 plus billion years, like our sun would live, it's very compact. And so the guy said if you were to visit a white dwarf and bring back a teaspoon, it would weigh 15 tons. In something, yeah, like about the size of maybe this. It weighs 15 tons. That's pretty compact. So one of the things about white dwarfs, which is kind of interesting, I think, is that the more massive they are, the gravity kicks in and it makes them even smaller. So a higher mass white dwarf is smaller. And the example your author has here is if you have a white dwarf that is 1 times the mass of our sun, to scale, notice what we're talking about here is you take something, the mass of our sun, and what's its volume going to be? The volume of the earth. Yeah. So the mass of the sun down to the volume of the earth. That's pretty dense, right? So yeah, that's yeah. But if you have a white dwarf that is more massive, instead of 1, it's 1.3. Notice what's its size? Smaller. I know it seems kind of counterintuitive, but gravity kicks in. So actually, 1.3 is kind of an upper limit for a white dwarf. So the thing about it is anytime you take matter and make that matter go smaller, increase the pressure that matter is got around it. What I mean to say is the atoms are closer together, so it's higher pressure. Okay, then the little molecules or atoms are going to have to go faster. So the problem is, so if we keep squeezing, they go faster, keep squeezing, they go faster. That's fine, but there actually is what we call the cosmic speed limit. We'll be talking more a little bit about that when we talk about what Einstein says. The cosmic speed limit. We said light travels very, very, very fast, and that actually is the fastest anything can travel. This is what we call the speed of light. What variable do we use for the speed of light? Right, the letter C, mc squared. C is light, the speed of light, yeah. So this is to say if you have a white dwarf, right, that is 1.4 times the mass of our sun, so it'd be smaller than the 1.31, wouldn't it? Okay. You can't get any more massive without something else happening. And that something else actually, I'm going to say, is to become what we call a neutron star. The 1.4 limit is called the Chandrasekhar limit. And at that point, it's normal mass. What I mean to say is, what does an atom look like? What's in the center? Nucleus, yep. And then it has, what's the nucleus have? Protons and neutrons. And what's outside the nucleus? Electrons, yeah. So by normal matter, I mean to say that basically in a white dwarf, it's the electrons are kind of repelling the other electrons from the other atoms, okay? So it's what we call electron degeneracy. Aha. So what is this? What's this look like? Two stars. There's letter B. Binary stars. Yep, this is just binary stars. And we ended the last chapter with this slide, actually, on Friday. So binary stars, are there very many stars that have companions?
Lots.
Yes, lots. And then we had the situation where, you know, the pair of stars might be aging differently. They started out with different masses. So the one that actually is the red giant, actually it's got the matter that's kind of swollen anyway. And what can happen is, like you see here, the matter from the red giant can be kind of siphoned off onto its companion. Now, does this actually, we're going to call this an accretion disk. It looks like a frisbee. See this guy who's getting new matter here? Okay, it looks like a frisbee. I don't know if it looks very hot, but it is hot. Okay, so that's matter that's kind of came from his buddy, and it's circling and getting closer to the companion star. We have a few different scenarios that is just like this. I'll tell you kind of, well, I'm going to walk you through it. Okay. All right, so you got the whole accretion disk. That might have been a word you had to fill in. That's the frisbee part. Okay. Okay, same thing. Can you kind of see the binary stars here? Okay, this guy's a swollen giant. This guy over here, the caption says white dwarf. You probably can't read it, but there's a white dwarf, a retired star here, and his companion. Well, the title of this says nova, nova, and that's one of the things I want you to understand. Nova is different than supernova. I'm going to talk you through that. Nova is just like this, where we have a white dwarf and a companion star dumping matter onto the white dwarf. That's a nova, okay? Now, what can happen is that retired star temporarily comes out of retirement. If you ever know somebody who retires, sometimes you see them out doing stuff, you're like, hey, I thought you were retired, okay? So, comes out of retirement momentarily, and what I mean to say is it begins nuclear fusion, but not nuclear fusion in the core of the white dwarf, okay? And the reason it can begin nuclear fusion is because it got new, fresh hydrogen from its buddy. So that fresh hydrogen from its buddy, actually, you can kind of see the difference between this one and this one. Can you kind of see the white dwarf? Does it look like it's bright? Okay, that means kind of the nuclear fusion that it began because of the fresh hydrogen. But do you think it's going to do that very long? No. It's just kind of a blip. It's called a nova event, and they're really kind of fun in the video we watched, we saw the guy with his fancy telescope and he, yeah. But you can see nova events occur for stars in distant galaxies. They're very energetic. Okay. And the cool thing about nova events is that they can reoccur, okay? So you figure that white dwarf, after it kind of blows off the fresh hydrogen in kind of uncontrolled nuclear fusion, okay, then it goes ahead and goes back into retirement. And you figure its companion is still swollen, fresh hydrogen, it can do it all over again. So that's kind of fun. The nova can reoccur. Oh, and by the way, this actually is showing you apparently a nova event. I'm not sure where it is. Well, maybe the caption says this is taken by the Hubble Space Telescope, and it's saying that blobs of gas were ejected from this nova event. Okay. What else we got? Aha. So now that was nova, and this is supernova. Okay, now, don't blame me. I wish they'd come up with separate terms, but do you guys remember the video we saw when a star has iron in its core? What happens?
It really exploded.
It's going to really explode, exactly. Now, we call that a supernova also, but that's different than what I'm going to show you here. Again, don't blame me. Okay? So that one with the iron core, that's actually, I'm going to do Roman numeral 2, type 2 supernova. This one is a type 1a supernova. So let's see what this looks like. Type 1a supernova. Look, you got your binary star system. It looks like we just looked at before. You got your swollen red giant and your retired white dwarf here. Okay. But what happens is not the kind of easygoing thing with a nova. With a supernova here, what happens is basically, is this right? Yeah. It gets enough matter from its companion that it goes past that limit, that mass limit. Remember I told you the most massive a white dwarf can be? Let's see, how do I want to say this? White dwarfs. Yeah, I'm going to do this. Okay, white dwarfs. The end result of a low mass star. The most massive it can be is, let's see, I'll put this, the mass has got to be less than or equal to 1.4 times the mass of our sun. Now, what's happened here is it's gone past that mass. So basically, it becomes very unstable, think of it that way, and in its instability, it does begin nuclear fusion again, but just temporarily. It can't sustain this nuclear fusion that's going on in its core. So that white dwarf that this happens to, it blows up. Okay, so this is a supernova. I'll put it at the top here, supernova 1A. You're like, well, where's 1B? Where's 1? Okay, so here we go. Supernova. We use the word type, T-Y-P-E, 1A. And I know it's like, well, how come the other was supernova? They're both supernovas. Okay. There we go. What else we got? Okay, so comparing the two types of supernova. Up here, the first little paragraph, I'm going to put, what's the symbol for iron? Fe, yep, very good. I'm going to put Fe core. Iron core explodes. Okay, and that is what we call a type 2 supernova. So the way I remember it, I don't know if this will help you or not, but this is the blowing up star. Let's see. And the kind of the cutoff for that is 8 solar masses as it's on the main sequence. So these guys are going to go supernova. What did I say? Type 2? Roman numerals? Okay. So I usually think that's the type of supernova I think of most, like a star blowing up. And that's actually the second one. You know what I'm saying? It's like counter. So the 1A is the companion, the white dwarf companion blowing up. Now, do all white dwarfs blow up? Nope. What do you need, and sometimes this is a test question, what do you need in order for a white dwarf to go out as a type 1A supernova?
Companion star.
Very good. That's the way that problem gets answered. You need to have a companion to dump stuff on you, to get, or dump stuff on it. Very good. Okay, cool. So I just wish they came up with something different. Like, really? So we can have 3 explosive events: novas, supernova 1A, and supernova 2.
I know, yeah, it would have been cool to have another name.
What's that?
It would have been cool to have another name, like.
I know. They're such cool events too. Okay. Now I won't put this on the test, okay? Because this to me looks like a very subtle difference. These are light curves. Now at the observatory, people, we've got this guy who can find anything in the sky. He finds comets, he finds supernova, okay, he finds nova events. He does his homework. And he's so good at moving that big Clark around. So those explosive events, they're bright for a while, but then they decay. So this is showing you a decay curve of the light. I think, I don't know what 400 days would be. I usually think of 2 weeks. Well, that's only like over here. Anyway.
400 days would be like a year and a month, I think.
Okay, thank you. Thank you. So it brightens, and maybe the 2 week I'm thinking of is kind of this up here, and then it decays, I'm not sure. But you can't see them clear 2 years out or whatever. Yeah, 365 days, right?
Yeah.
So they decay over time, and there's a subtle difference, but whether it's the white dwarf, the 1A that blew up, or if it's a massive star that blew up, there's a subtle difference. So, okay, so nova or supernova 1A, okay? They both involve a pair of stars, okay? The supernova will be much brighter than the nova. The supernova 1A will be much brighter than its analog, the nova. Let's see. And with the nova, they can reoccur. Sometimes that'll be one of my test questions too. Okay, nova can reoccur. The supernova where the massive star blows up, that cannot recur. And the supernova where the white dwarf blows up, that cannot reoccur either. So these supernova where basically it got dumped on to exceed 1.4 solar masses and it comes out of retirement catastrophically, it does not leave a nugget behind. Now we're going to be talking more about this. I can't see this, can you? These, when a star begins fusing iron in its core, it's near the end. When it runs out of silicon to form carbon, I think it is, and it blows up, one of 2 things are left behind. You're either going to get a neutron star or you're going to get a black hole. And notice how I went ahead and wrote them this way. Okay? If it's lower mass, you're going to get a neutron star. If it's higher mass, you're going to get a black hole. If it's the situation with the companion white dwarf blowing up, supernova type 1A, nothing's left. Okay, nothing's left. Okay. Very cool. Well, that's a good thing to kind of lead over here. This idea of, with the supernova type 2, okay, the massive star has lost the battle and blew up, okay. You do get, in addition to kind of this nebula stuff, okay, because of it blowing up, you get something in the middle that's either a neutron star or a black hole. So let's look at neutron stars first. What is so cool about neutrons? Well, a minute ago, you guys told me that a normal matter, a normal atom, okay, has a nucleus and has electrons out there, okay? In the nucleus, we have protons and neutrons. I'll emphasize neutrons. So what happens is, and I remember how I was kind of making stuff more and more dense the other day. Can we make it really dense? Okay, what happens is the conditions as the star goes out, the gravity and pressure actually make the electrons and the protons combine to form neutrons. You already had neutrons, now you have more neutrons, basically. Okay, so it's not normal matter anymore. So if we were to visit this neutron star, it would be very dense, okay, and its matter would be very different than we're used to. Sure, like, one of the things I want to do in this course is try to convince you how they know, they being astrophysicists, how they know what they know. Okay, you can sit do paper and pencil and theorize what these objects are going to do, but until you go out and connect your observations with your theory, I don't buy it necessarily, neither do you. But actually, we've seen signals of neutron stars. This is Crab Nebula. This is what we call the supernova remnant that's left after a supernova type 2 event. In there is an object sending this signal that you see in red. Okay. Let's see, 5 seconds, 6 seconds. So about 1 1/3 seconds, it sends a blip every 1/3 second. Blip, 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 blip. And this is what the guy said the other day on the video called the kind of the lighthouse sort of thing. This is, I'm kind of building. Is it warm in here or is it just me?
It's a little warm.
Kind of stuffy. Okay. So in 1967, Bell Labs, I think Bell Labs, Jocelyn Bell, actually saw this signal coming. Okay, and one of the cool things is if you go back to 67, the whole UFO thing and looking for intelligent life out there. So what they thought they had right away was a signal from intelligent life. And so actually she called this an LGM source. They, LGM. This was LGM1 because it's the first one they found. LGM, gotta have sense of humor, stands for Little Green Men. I just think that's so funny. So, but the thing is, when they started looking for these, they found more sources that were giving that repeated signal. You're like, oh man, somebody's sending us kind of like a Morse code sort of thing or something. And as it turns out, it's something very natural, not any little green men at all. So the reason neutron stars give us this signal, by the way, the signal is what we call a pulsar. So somewhere in your vocabulary, you're going to have to link neutron star with a pulsar signal. And this is where, like I said in the video, I think he did a good job. So basically, we've talked about magnetic fields, okay? And magnetic fields can actually send out, this actually has a jet of energy coming out kind of the center of the magnetic field in both directions. And so, or where the poles are, I guess I should say. And then so if you guys are Earth, and if this thing is swinging like this, you're going to see it, see it, see it, see it. So it's kind of like a lighthouse. So whenever it's in your line of sight, you see it. It swings around, you don't see it, you see it. Now 1.3 seconds for something that's, I don't know, it's very massive, that's some crazy rotation. Okay. So that's a pulsar and that's a neutron star. And it's the remnant, or not the remnant, but the core of a massive star that blew up. I just think that's so cool. It's like, how many times can you see this figure? Okay? Okay, so binary, right? We have our retired white dwarf over here on the right, and our swollen red giant over here on the left. Okay? Well, now actually I called that a white dwarf, but I'm switching it up a little bit. Instead of white dwarf, and it probably says it on the slide, I'm going to put neutron star. I just think so no longer white dwarf. So a neutron star is even more compact, more dense than a white dwarf. So its gravity is more crazy, and we haven't even gotten to black holes yet. So you kind of see this, it starts with letter A. What's this thing? Looks like a frisbee? Accretion disk. Yeah, that's the accretion disk, exactly. So kind of like we had before, it's kind of a nice toasty place. But here, if this is a neutron star, what we can get actually in the accretion disk is a crazy bit of energy, even more than the accretion disk of a white dwarf, and it's an X-ray burst. So if you think of your cousins, remember X-rays are pretty energetic. And what an X-ray burst is, as I understand it, is an accretion disk where you basically get such that nuclear fusion can occur in the accretion disk. Yeah, a sudden onset of fusion in the accretion disk. So that's it. That's another way we know what's up there. Okay. So we said white dwarfs can't be more massive than 1.4. That's called the Chandrasekhar limit. 1.4 solar masses. And neutron stars, their mass has to be less than or equal to 3 times the mass of our sun. Okay. So here's the deal. If you get something that's more massive than 3 solar masses, and it's the thing after a star blew up, okay, then what happens is that mass then, how do I say this? Gravity pulls that mass in on the mass. Gravity pulls that mass smaller and smaller and smaller, so it creates a black hole. Now I need to describe what black holes are, okay, but it creates a black hole. So finally, I have some other numbers up here. We said if it's a high mass star, you're gonna get a supernova type 2 event. We said that. It's gonna blow up. High mass being 8 times the mass of our sun or greater. Now I have another threshold here. Between 8 and 25 masses of our sun, as it's a main sequence, these guys are gonna end in neutron stars after they blow up. And these guys are going to end in what we call stellar black holes, or black holes. I hope that makes sense. So we kind of have one more kind of something to add up there. All right. So black holes. I brought in some videos to try to kind of hopefully animate it and show it to you. So down here at the bottom, this last word, this says space-time, okay? Einstein did a lot of theoretical things. You're like, oh, great Einstein, that's just crazy. A lot of his theoretical stuff, they proved, I don't know, as he was alive since his death. So they've proved this. So I haven't talked to you guys about this yet, have I? So as you're walking around, you think, well, I am relocating myself in space. I'm going from this point, point A, to this point, point B. You know, X, Y, Z coordinates, that sort of thing. But what Einstein says is that the space we occupy and move about and time, space and time actually are combined into what we call, and I use the word fabric. I know this is just, I usually use, it's the fabric of space and time that are related to each other. It's so cool.
Isn't there something like called the space-time continuum?
Yes, I think so. I think that sounds like Star Trek, the space-time continuum, but you know, we say that they're not related, but they are definitely related. Okay, so that being said, we can kind of think of objects like us, or more importantly, like planets or stars or white dwarfs or neutron stars or black holes as being objects in this thing we call space-time. And so this gray area with the crossbars and that sort of thing is trying to show you the fabric of space-time. Okay, and we've talked about how planets orbit stars, our planets orbit the sun, okay? And actually, if you take the star and put it on the fabric of space and time, it literally creates a dent in the fabric of space and time. The more dense or compact the object, the bigger the dent it creates. So we have a few scenarios up here. You know, you could have something in the middle up there, that could be like a planet, no dent, okay? Something a little more massive, okay, it's got a dent there. And so this idea of orbiting, gravity, having objects orbit other objects, that actually goes along with this concept of space-time. This one down here, okay, this actually is what the fabric of space-time would look like if a black hole were setting on that part of space-time. So this is why, and I think one of my videos is going to talk about this idea of a wormhole, because black holes make a dent, not just a dent, make a hole in the fabric of space and time that they're resting on. And also, to create a black hole, all you need to do is basically take matter and compress it down to the point where if you're on top of that matter, you would have to go faster than the speed of light to escape the gravity that object, okay? That's a black hole. Okay. I'm almost getting to my videos. So have you heard of like escape velocity? That's how fast you need to be going in order to leave the thing you're trying to leave. If you're leaving Earth, the Earth has a gravitational pull on you. Okay, so we have a certain escape velocity associated with Earth. If you're trying to leave a black hole, you can't go fast enough to leave that black hole. So what this says is how fast you need to go is a function of m stands for mass and r stands for radius. So if you want to increase your escape velocity, do you see where you can increase your mass, okay? But do you see where if you decrease your radius, then that increases your escape velocity? I don't know if you see that. So when I'm doing this, I'm decreasing my radius. That's how that works. Okay, so let's talk Earth. Let's talk turning Earth into a black hole. Sounds like a science fiction. It does sound interesting. Don't try this at home. Yeah. Well, you can do the math and all that, and if you were to take how big Earth is and to make it the size of, let's see, what the radius, to shrink our radius down to less than 1 centimeter. Keep all our mass, but shrink it all down to, to 1 centimeter. Now, to me, what's going to happen when you do that is you have normal mass now, right? And then the white dwarf still is normal mass. You have electrons repelling each other, okay? But to me, along your shrinking process, you would actually create kind of a neutron star thing, and then you go over here, and it would be a black hole. Let's see what we got. Where's all my things, my links? I wonder if I opened the wrong one. I know I put links here, and now they're not showing up. Well, there's a couple. All right, maybe they're coming. All right. So a few terms associated with black holes. You're going to hear people talk about the event horizon. And the event horizon is kind of the point of no return. It's kind of, the event horizon is around the black hole. The Schwarzschild radius is simply from the black hole out to the edge of the event horizon. It's the radius of the black hole. So let me draw a picture. You're going to see a picture here in a minute. But if this is my black hole, and then this is the event horizon, And then the Schwarzschild radius is just like the radius of a circle. So this is the Schwarzschild radius. Okay, so that's it. And what this says is that the more massive your black hole, the bigger your Schwarzschild radius. So this is where, like, if you were a spacecraft here, you could still leave your black hole. That's why, yeah, so you could go visit, just don't get too close.
Yeah.
Yeah. If your spacecraft here, you're not leaving. You cannot leave. Yeah. Stuck. You're
It's
stuck.
like magnets, kind of.
Gravity.
Not literally, but
Gravity.
you know, like the
Oh.
pole of a magnet, and you get
Yeah,
too
that's
close and
true.
it's-
That's
it's
true.
sticky.
The magnets are like, there's a point where you're just
You're
there.
just going there.
It's gonna happen, right. Black hole warps the fabric of space and time, okay? So, yeah. Nothing can escape if you're within the event horizon. And part of that is if you're here, all of this right here, the escape velocity, so V escape is greater than C. What's speed? What's C?
The speed of light, or
Yep.
light, light?
Speed of light, yep. You'd have to go faster than the speed of light if you're there, anywhere there. Let's see, it increases the hole's mass. So, yep. So if something falls in, I think that's what I was trying to say here. If something falls in, it actually adds to the mass that the black hole has.
It adds to it?
Yeah.
So it's there, kind of, but not really? Kind of, 'cause it
Yeah,
has
you mean the
acid?
thing that it ate is
Yeah.
still there? Right. The thing that it ate is still there.
Oh.
I know.
But of course, it's not going to be the thing anymore.
Yeah,
Right.
exactly, that's just weird. I was like, when it goes to the black hole, does it go somewhere? But it
Nope.
doesn't.
It's in the mind.
No. And then the thing, like in the middle, the black hole itself is called, it's called the singularity. So, how do I say this? You know what this sign is, right?
Infinity?
Infinity, yep. So we say that at singularity, the density is infinitively large. And if you know what density is like how squished something is or how fluffy something is. Where's all my things? They must be coming up. Okay. So we shrank the Earth down into a black hole. It's 1 centimeter, right? If we shrank the sun down to a black hole, that would be bad because we don't have the light. That would be really bad. Yeah. But the thing about it is if somebody were to do something funky with the sun and basically take the matter of the sun and squish it down to the density where it became a black hole, we'd be okay. I mean, we'd stay, our orbit, as I understand it, would not change. We'd have an issue if we get across the horizon. So I think this is kind of showing you, now this is not the sun as a black hole, but this is just the sun. And can you see, it didn't make a hole in the fabric of space-time, but it's making a dent. I like to kind of think of like if you have a sheet and somebody's holding the four corners and you put something on it. That's kind of the dent it makes. Fine. Okay, let's see what these look like.